So I want to talk about this problem, perfect squares. It's a pretty math-heavy problem, but the time complexity for it is really interesting, and that's what I want to focus on. So the problem says, given an integer n, return the least number of perfect square numbers that sum to n. So 12 would be 4 plus 4 plus 4, aka 3. 13 would be 2, because you can get away with 4 plus 9, and so on. So there's a bunch of solutions for this problem. There's like greedy, depth first search, breadth first search, whatever. I'm really interested in just the hard math approach. And ironically, I'm not actually that interested in the math behind it. I don't really care about all these conjectures and all these theorems and stuff. I want to focus on the time complexity of it. That being said, there's a couple of things we need to know. So straight up, everything can be represented as a sum of 4 or less squares. So if we go back to our test cases, this output is never ever going to be greater than 4. It's always going to be 1, 2, 3, or 4. And then the second thing to sort of cover before we look at the code itself is this specific theorem, this 3-square theorem that says if it's of this form, which looking at it briefly is a power of 4 plus 7 above a multiple of 8. I'm sorry, a power of 4 times 7 above a multiple of 8. That's my bad. If it's of this form, it can't be composed of a sum of 3 square numbers. It has to be 4. So, and I don't really care about how they found this, what this means. I barely even care about this equation itself. But it is what it is, and we're going to use it. So the thing I want to ask is, why in this code do we check in this order? This code is very straightforward. It's just, is it the sum of 4 squares? Is it the sum of 1 square, 2 squares, 3? But why are we checking in this specific order? Why are we saying, oh, is it the sum of 4 squares? Why not 4, 3, 2, 1? Or why not 1, 2, 3, 4? Because I feel like 1 would be the simplest. It is intuitively what makes sense. 1, 2, 3, and 4. This code is kind of the most complicated. This is kind of the least complicated. I mean, it just refers to this helper function, but that's where the time complexity comes in. So what I want to do is I want to go through and look at the time complexity of each of these code snippets, because they are pretty self-contained. It's just, if this return 4, if this return 1, if this return 2, and then by process of elimination we get to return 3. We don't really have to check anything, because if it's not any of the other ones. And that pretty much answers how this code works, or how it operates, why we get to just return 3 without checking anything at the end. But let's start with 4. So it's saying if n and 3 equals 0, and this is sort of a bit manipulation, but this is checking, are the last 2 bits representing n, those 1/0s in the binary representation of n, are they both 0? AKA the 1's place is 0 and the 2's place is 0. That's the only way this can be satisfied, and what that means is n is a multiple of 4. So for example, 1, 0, 0 is 4. 1, 1, 0, 0 is 12. Those are both multiples of 4 that end in zeros, aka 12 and 3 is going to be 0, 4 and 3 is going to be 0, 16 and 3 is going to be 0. So if this is true, while this is true, bit shifted over by 2, which is another fancy flashy way of saying divide it by 4. Bit shifting anything over by 1 is dividing it by 2. So bit shifting over by 2 is dividing it by 4. And then finally, we're left with a number after that, once we've divided this by 4 as many times as we can, which is essentially, if we look back at this equation, satisfying the power of 4 part. We're taking that out. We're saying as long as it's divisible by 4, divide it by 4. So now what we're left with, this n, is just this equation. It's 7 above the next multiple of 8 is all we care about checking. And that's exactly what we check. We say, okay, is n and 7 equal to 7? And it's kind of the same fancy bit checking as above, where we're saying, is n 7 above the next multiple of 8? If n and 7 was 0, that would mean n is a multiple of 8. Just like n and 3 is 0, n would be a multiple of 4, and so on. When n and 7 is 7, that means the last 3 bits representing n are 1, 1, 1. Yeah, so then it satisfies this if this winds up being true. And when that's the case, we get to just return 4. And then the rest of them are way less complicated. So we're just checking if it's the sum of one square, if it itself is a square. So we call this little helper function, because we use this later as well. We just say, take the square root, convert it to an integer. If that squared is n, then great, n is a perfect square. And we get to return 1, because we just check, hey, is n a perfect square? If so, then we immediately return 1. For 2, it's a little more complicated. We say, for every number in the range between 1 and the square root of n plus 1, if that number is a square, return 2. Sorry, not if that number is a square. If n minus that number squared is a square. So we're just checking every square between 1 and the square root of n. And then we're saying, hey, subtract that from n. If what's left over is a square, then we found 2 squares that add up to n, so return 2. And then again, by process of elimination, we get 3. So something that we can start thinking about is, what are the time complexities of each of these? This time complexity is easy. This is arguably O of 0 time complexity. It's not even O of 1. You're literally just returning a value. This, however, we have like a for loop and stuff. We don't really have that up above. But at the same time, we have a while loop up here, which is awful close. So why don't we have this be, hey, let's check for, is n a square, and then check 2 and then 4, or 4 and then 2? Like, why is 4 above 1 here, despite being a loop? And this is where we get into specific mathematical algorithms. So that'll be the first thing that I'll answer. Why do we have 1 not as the first thing? And that gets to specifically the math.square-root function. So this function, it's clean and pristine, we get to just call it, but it's not O of 1. If we're talking about with regards to n, let's say n was 1,000,000 digits long. We could, we could claim, oh, well, if that's a native data type or whatever, then that's still O of 1. But realistically, with regards to n, the square root function takes time. If you're mathematically deriving it, it itself is O of square root of n. But what all these functions do is they just perform a binary search up to a specific value, up to like the 100th decimal or whatever. And a binary search is log base 2 of n. So what that tells us is this square root, calculating the square root, is log base 2 of n. To find it, which means that checking this is log base 2 of n, to see if it's a square. And if we look up above, this is actually a pretty immediate comparison. What are we doing in this while loop? Because this is the number of operations we have. This is O of 1. We're just checking flat out, is n and 7 equal to 7, and return something. That's one operation. It's a very simple bit operation, checking 3 binary places on the computer. This while loop, though, interestingly enough, we're saying while it's divisible by 4, divide it by 4. So it's going to, the larger n gets, the amount of times that this while loop loops is going to be log base 4 of n. Because if this said while n and 1 equals 0, if this was while n is odd, or sorry, while n is even divided by 2, if it was something like this, this would be log base 2, because it's just, every time the loop goes, we're dividing n by 2. Yeah, but this is log base 4. And that actually immediately answers why 4, checking to see if it's the sum of 4 squares, is above checking to see if it's the sum of 1 square. Because this function, a binary search, is log base 2. This little pseudo function is log base 4. So this is going to have exponentially less loops in it. So let's look at the sum of two squares. What this one's doing is it's iterating through. Immediately we can see its calling is square. So however many times this loops, it's calling this function, which itself is log base 2 of n. So this is log base 2 of n, and it's calling itself the square root of n times, because it's just iterating from 1 to the square root of n plus 1. But, you know, for big O notation, this is, for all intents and purposes, the square root of n. So this is sort of the square root of n times log base 2 of n, which is much, much more than these. Even if this were just the square root of the square root of n, the square root, like, with big O notation, O of the square root of n diverges way faster than O of log base 2 of n. If you have the square root of 1,000,000, that's, what, 1,000? But log base 2 of 1,000,000 is like 30 or 20. And then the last thing to look at is, why are we not checking 3? And the answer is that would be much more complicated. We can show that n is the sum of 4 squares instead of 3, but it would be very difficult to show that n specifically is the sum of 3 squares. So we leave that last, because if we had 3, 4, 1, 2, we could take this out and we could just say return 2, and then have whatever 3 squares code up here. But the problem there is that this 3 squares code, we don't have to do this square root of n times log base 2 of n operations anymore, but we would have to do the 3 squares code, which would be more. So just because this takes the most time, we choose this one to use process of elimination over calculating the actual situation where it would be the sum of 3 squares specifically. So to recap, we have looked at the time complexity of each of these snippets. This is log base 4 of n, because it's a loop that divides by 4 every time. This is log base 2 of n, because it references this, which finds the square root, which is a binary function, or a binary search, which is a log base 2 function. And this is log base 2 times the square root, because it iterates through the square root of 2 times, or the square root of n times. And to connect this all, we can see that this takes the shortest amount of time, log base 4. This takes the second shortest amount of time, log base 2. This takes the longest amount of time of the stuff we bother to calculate, log base 2 times square root of n. And this one, we don't bother calculating it because it would take the longest if we did. So we can see we just do the quickest thing first. The reason being, you know, if there's a number that we're given that's the sum of 4 squares, we don't really want to have to iterate through everything else. If we checked every single number, if it was a square itself, this would run significantly slower, because the numbers that aren't squares would have to perform a more time-intensive operation, time-intensive part of the code, before reaching the part of the code where they can return, as opposed to having sum of 4 squares first. Things that are perfect squares, this takes a lot less time for them to get through than this. So when they return, that's added less time to your code than if you'd had this first and you were iterating through cases where non-squares had to still check to see if the number was a square. And that's true for sum of 2 squares too. If this was first, then you'd have to do something pretty time intensive compared to everything else. regardless of what the actual answer was. And the final piece to it is that not that many numbers are perfect squares, and not that many numbers are even the sum of 2 squares. The vast majority of numbers are the sum of 4 squares. So it's actually really convenient that this is the least time-consuming piece of the code, because this also covers the most cases. So I think there's a world where if, for example, this sum of 4 squares was, this person hadn't found this theorem and we had a more inefficient theorem that's, let's say, log base 1.5 of n or something that takes more time than this, we might still want this first, just because statistically most numbers are going to be the sum of 4 squares. They're not going to be themselves a square. But we don't really have to worry about it when organizing this code. But it is something to think about, that this layout is the most optimal layout, not only when you consider all of these different cases, that it's the sum of 3 squares, 2 squares, 1 square, or 4 squares, not only if you consider all of those equal possibilities, but also if you take into account the fact that those aren't equal possibilities and there's a lot more sums of 4 squares than 1 square. Even in that case, this is still the quickest way that this code can run. I could see some, like, let's imagine 3 squares are by far the most common thing. In that situation, you might actually want this code up top, even if it takes the longest time. You might want to check, is the number the sum of 3 squares? If, let's say, 99.99% of numbers are the sum of 3 squares, it might not matter that everything else takes less time. Then this really would just be, oh, well, in the end, process of elimination, return 2. And then you have some really big complicated thing here that's like O of n or something horribly inefficient, considering we're doing math here. But I guess they've probably checked that and they've gone, nope, not 99% of numbers are the sum of 3 squares. There's a more even distribution than that. So it's worth it to have these more efficient algorithms for checking if it's the sum of a different number first. But that's what I wanted to go over for this problem. 2 big things. The first big thing being, hey, what are the time complexities of each of these? Log base 4, log base 2, log base 2 times the square root of n, and nothing. And then why does that make us want to set it up in this order? That, hey, the fastest one should go first. That way we know to dip out of this function and just return something early faster for things that are the sum of 4 squares. And then the second thing being, statistically, not everything is 1 square, and we can sometimes optimize our code inherently based off of patterns in numbers, such as, hey, not everything is, there are not the same number of squares as there are sums of 4 squares or sums of 2 squares. And I'll leave it with a question, which is kind of perplexed me for a minute when I was looking through this problem. Why do we never reset n here? We bit shifted over by 2 a bunch, so we divide it by 4 a whole bunch of times, but then we just go on with the rest of the code. And we were just working with a different number than we're given for all of this. We're checking is square of another number that's not what we were given. Which I think is a pretty interesting little, that's more mathy, but that's a pretty interesting little thing to think about for this problem. Anyway, thanks. Bye.